to the density matrix, right? Like, we've only been describing thus far what the density matrix is, and we have to try and understand what happens when you let it go, basically. And the way we start this is we go from the time-dependent Schrödinger equation, which is given up here, just at the time derivative of psi. Right, that's what it is. And then you solve the equation, and you can basically do this for the bra and the ket if you wish. So for the ket, you get the exponential of the operator if you solve this. I don't know. Should we go through and solve this? It's easy enough, I think. Are you interested in seeing that?
No, I think so.
Right. And so you get the time-dependent of the Schrödinger equation of the bra and the ket, and then you just split these two results together, and then you basically what you have is a density matrix, how we expressed it earlier, right, as a function of time. And we know now that all we need to do is, if we have some Hamiltonian, to multiply the density matrix from the left to the right with, I guess, these two terms. And then, yeah. Now, I guess all we have to do is find out how to easily evaluate this equation, right? And luckily, in some cases, it's very simple.
I have a question. So if the density matrix describes the distribution between the two states, alpha and beta, or not quite?
Right.
Okay.
So, and this is exactly why we're introducing the density matrix in the first place, right? So if you are only concerned with describing alpha and beta and the distribution between the two, you would think that if you have the coefficient that describes alpha and the coefficient that describes beta, you would have enough information.
Mm-hmm.
But because these coefficients can be imaginary, it is helpful to have the square terms. Mm-hmm. And this is what the density matrix is. Mm-hmm. So I guess I can go back to the slide where we introduced the density matrix. Here, right?
Right.
So the distribution between alpha and beta
only
is the coefficient 1 and the coefficient 2, right? But this is a little bit more useful, as you will find out later, because it includes these square terms.
Right. This is a simple, maybe a ridiculous question. Does the distribution between the two have to equal 1? I mean, does that make sense? Does the sum of the distribution have to equal 1? Like, either you have it. Yeah. I'm thinking of like splitting up apples between, the states alpha and beta.
Well, the trace has to equal 1.
The trace has to equal 1, right?
The trace of that matrix has to be 1.
Okay. Summed to 1.
Because it's just this thing where like the amplitude of the wave function has to equal 1, so that means the squares the squares.
Right.
The square modulus has to equal 1, or the sum of the square moduli has to equal 1.
You define your basis state such that whatever you're measuring has to be in some state at any given time.
Right. Okay. Great. Thanks.
I think that one of the super useful things about the density matrix is that you can take a bunch of things that are in different states and sum them up easily, whereas it's not that easy to do that with straight wave functions too.
So I guess the reason why we're switching to commutators is because before we have seen this expression, and in this expression to be able to easily evaluate it, it always is very helpful to know what the commutator between the Hamiltonian and the density matrix is. Okay, so let's just basically remind ourselves what is a commutator, what are properties, and stuff like that. So the commutator of two matrices is basically defined above, and so if their order doesn't matter, then this is going to be 0, and that's when you say that two matrices A and B commute. So when AB minus BA is 0, then they do commute. And
so maybe it's like, to clarify, it means that AB equals BA. Actually, which is not always the case, right? So
Right.
just to clarify. Sorry.
Yeah, no, it's perfect. Right. And so, I guess before going into other cases where it's non-zero, I wanted to basically show what happens if, like, basically in this expression, right, where we have the Hamiltonian and the density matrix, if they do commute, right, what happens then? In that case, I guess it's very easy to evaluate this because if they commute, their order doesn't matter, right? And you can basically just switch them around whichever way you want. So you can basically put this exponential together with this exponential, and then if you put the two exponentials together, a minus a is going to be 0, and then basically your result is going to be just b left over. Okay, and what that means physically is that there is no time evolution if the density matrix and the Hamiltonian do commute. Right? So
Another mathematical property of commutation that we should talk about maybe is that it means that if A and B commute, it means that they have a common eigenbase. Does it? I don't know if it makes sense to say that. So we can diagonalize them in the same base, and that's actually the reason why if A and B commute, then exponential A and exponential B commute, and A and exponential B commute, etc., etc.
right. So, but now let's turn our attention to a little bit more interesting, I guess, scenario, which are these kind of cyclic commutation relationships. So, if the commutator of A and B, say, is in cyclic commutation relationship with another operator C, so is it clear to you what cyclic commutation means? So let's write it out. So cyclic commutation is when commutator A how do I do this? Then so the important thing here is that they be in the same order, right? You have A, B, C, right? And it's cyclic. So here, I already messed it up, I guess.
No, it's right.
Oh yeah, that's right. A, B, C, and then here, A, B, C, right? Is it actually in general true that if you were to write this in a different order, say B, A, is then equal to positive IC.
Yeah, this is true because it's a commutation. Like the commutator BA equals minus AB by definition of the commutator. So it makes sense.
With like that, it's like the Levi-Satie is similar. It's like A, B equals C epsilon I J ABC.
It all expresses the same thing, though. And it is very useful to know this. One thing that is important to know is that, say, if this is true, right, it does not necessarily mean that this is also true, right? So really, all of them have to be true for this to be a cyclic commutation relationship.